Hello, welcome to a new lesson. Today we are going to show the Leibniz theorem, right? And to get some inspiration of how to do that, we are going to speak about what happens when we have a normal binomial. I mean that, for example, if we have a plus b to the n, well, we know that by the Newton's rule, this is equal to the sum from k equals 0 up to n of n choose k, a to the n minus k, b to the k, right? So for example, we know that a plus b squared is equal to a squared plus 2ab plus b squared, and maybe a plus b to the third power is equal to a cubed plus 3a squared b plus 3ab squared plus b cubed, right? So I'm showing these two first examples to tell you that well, the Leibniz theorem is about the derivatives of the product of functions, right? If you have a function defined as the product of two functions, and you are interested in taking the nth order derivative of that function, well, it turns out that when you do that, you get some expressions that are very similar to these structures that we have here. For example, let's define that f of x is equal to u of x times b of x. And then what happens if we want to take the first derivative? Well, let me use this notation as one in between a parentheses, right? For denoting the first derivative of x, which is going to be u prime b plus b prime u. And then, for example, the second order derivative of x is going to be u double prime b plus b prime u prime plus b double prime u plus b prime u prime, right? So as you can see, this will have the next structure, u double prime b plus 2 times u prime b prime plus it will be u b double prime, right? So you can see that it has a very similar structure to this thing that we have here, right? It's like just switching the exponents for the order of the derivatives. Okay, let's calculate the third derivative of x for you to watch it more clear. So if we take the derivative with respect to x of this, we will get u triple prime b plus u double prime b prime plus 2 times u double prime b prime plus u prime b double prime, and then plus u prime b double prime plus u b triple prime. Okay, so as you can see easily, this is u triple prime b plus 3 u double prime b prime plus 3 u prime b double prime plus u b triple prime. Again, it has a very similar structure to this thing that we have here. Okay, so if we keep doing this, we'll see that the structure actually holds. So that is a motivation to define the nth order derivative in terms of a very similar expression to the binomial expansion from Newton, right? Okay, so what will that be? Well, actually, we just need to switch the exponents for derivatives, right? I mean, the n minus k exponent will be actually the n minus k derivative of the function. So that can be seen as follows. If f of x is equal to u of x b of x, then the nth order derivative of x is going to be the sum from k equals 0 up to n of n choose k, u, well, the n minus kth derivative of u times the kth derivative of b, right? Just by switching the exponents for the order of the derivatives. Okay, so this is just like an assumption that we are doing, right? We are taking into consideration that maybe the nth order derivative of f can be calculated with this formula over here. So we are going to use the method of mathematical induction to show that. So we are going to consider that it is true for n equals m. So that means that the m order derivative of f is equal to the sum from k equals 0 up to m of m choose k, and the m minus kth derivative of u times the kth derivative of b. Perfect. So we are going to take this as a true, and we are going to see what happens when we take the case where n is equal to n plus 1, right? So if we have the m derivative of f, to get the n plus 1 derivative, we just need to take the derivative with respect to x again, right? And we are going to do that to this expression. Perfect. So for n equals n plus 1, we will get that the n plus 1 derivative of f is equal to, well, the derivative with respect to x of the sum from k equals 0 up to m choose k, u to the m minus k, b to the k, like this. Perfect. Notice that, well, this is just a constant, and we can take the derivative operator inside of the sum. So this will be the sum from k equals 0 up to m choose k, and then, well, the derivative of this product, right? Perfect. So if we have, for example, the m minus kth derivative of u, and we take again another derivative, well, we are going to get that this will be the m minus k plus 1 derivative, right? And in this case, if we have the kth derivative of v, if we take another derivative, we will get the k plus 1 derivative. So, and noticing that this is a product, we will get that this is the m minus k plus 1 derivative of u times b to the k, and then plus u to the m minus k, b to the k plus 1. Okay, perfect. So what I'm going to do here to see the process, I think, in an easier way, I'm going to split this to, this sum into two sums, right? So this will be the sum from k equals 0 up to m choose k, u to the m minus k plus 1, b to the k, and the plus the sum from k equals 0 up to m choose k, u to the m minus k, b to the k plus 1. Okay, perfect. And I think you should already know that the goal of the method of induction for demonstrations is to show that the structure of the formula remains the same, but only switching the m for the m plus 1, right? So we need to show that the new expression will be equal, but just instead of having m, it needs to have an m plus 1 element, right? So what we need to show, let me write it explicitly, is that the m plus 1 derivative of x is equal to the sum from k equals 0 up to m plus 1 of m plus 1 choose k, u to the m minus k plus 1, and b to the k. So this is the goal. I mean that, and this means that if the proposition is true for m, and it is true for m plus 1, well, now it will be true for every n, right? So I'm saying this because that's a motivation to generate an m plus 1 term in both sums. Actually, for example, if you notice this element, u to the m minus k plus 1, well, it already has an m plus 1. So we still need to generate an m plus 1, for example, over here, right? Okay, so that is what we need to do. So we will get that this is equal to the sum from k equals 0 up to m choose k, u to the m minus k plus 1, b to the k, plus, and what we are going to do here is that, well, you know that you can reorder the indices of a sum, right? Recall that we need to generate an m plus 1 everywhere there's an m. So we will be interested in getting the index here, the upper index, to be m plus 1, right? So that means that we need to sum a unit to the indices of the sum. And you know that whenever we modify the indices of the sum, we need to do the same thing over here, but with opposite sign. I mean that if we sum +1 over here, we need to subtract that 1 wherever we have the k on the sum, right? So let me do it for you to understand it in a more clear way. So this will be the sum from k equals 1 up to m plus 1 of m choose k minus 1, right? U to the m minus k minus 1, b to the k plus 1 minus 1, right? Recall that what we need to do is to subtract the 1 wherever we have a k. So as you can notice here, if we multiply this minus by this k and this minus 1, we will get minus k plus 1, which is what we were looking for, right? To get an m plus 1 term. And here, well, this minus 1 and this plus 1 will be cancelled. So we just get the k derivative of b. Okay, perfect. So notice something. This sum finishes at m plus 1, and this sum finishes at m. So if we split this sum into one sum and the last element, well, this sum will be only up to m, right? And it will have the same index that this sum has. And you will see why we will do this trick. Then this sum starts at 0, so we are going to develop the 0 element to get the sum from k equals 1 up to m. And then we will be able to get the same indices on both sums and to reorder the expression again. So this will be m choose 0, u to the m minus 0 plus 1, b to the 0, right? And then plus the sum from k equals 1 up to m choose k, u to the m minus k plus 1, b to the k. And then we will have plus the sum from k equals 1 up to m choose k minus 1, u to the m minus k plus 1, b to the k, and then plus the last element, which corresponds to the m plus 1 term, right? So what is that? So it will be plus m choose m plus 1 minus 1, u to the m plus 1, actually m minus m plus 1 plus 1, and b to the m plus 1. So notice something. This is 0, right? And we have m choose m here. So this is only b to the m plus 1. Okay, so if we rewrite everything, this will be m choose 0, which is equal to 1, u to the m plus 1, and b to the 0. But b to the 0 is, of course, just b, right? Recall that this is the 0th derivative of b. So the 0th derivative is just the function itself, right? And then these two sums can be put together, right? So looking that we have the same indices. And actually, notice that these two elements are the same. So they are like a common factor. So we will get plus the sum from k equals 1 up to m of u to the m minus k plus 1, b to the k, that multiplies, well, m choose k plus m choose k minus 1, like this. And then plus a last element that, recall, it is u to the 0, right? But that is u, m choose m, which is 1, and then b to the m plus 1. Okay, perfect. Okay, now we are going to be interested in calculating what this is. So we have m choose k plus m choose k minus 1. So to do this, we are going to use the definition. So this will be m factorial divided by m minus k factorial plus m factorial divided by m minus k minus 1 factorial, and then k minus 1 factorial over here. And let me write this as m minus k plus 1. Perfect. So we are going to see this as m factorial divided by m minus k factorial plus m factorial, and then this will be m minus k plus 1 times m minus k factorial. Yeah, recall that all this is exactly this thing that we have here, right? Just by taking one element of this product out. Okay, and then this k minus 1 factorial, well, it will remain the same, k minus 1 factorial. Recall that to get the same denominator on both expressions, we can take this k factorial to be equal to k times k minus 1 factorial, right? Just to get this k minus 1 factorial in both expressions. So that means that we can take a common factor, so like m factorial divided by m minus k factorial, and then k minus 1 factorial, and this multiplies 1 divided by k, and then plus 1 divided by m minus k plus 1. So this is equal to m factorial m minus k factorial k minus 1 factorial, and then m minus k plus 1 plus k divided by m minus k plus 1 times k. So this k is cancelled. Then we have m factorial times m plus 1 divided by, well, recall that this k with this k minus 1 factorial is equal to k factorial, right? So we have k factorial over here, and this m minus k plus 1 times m minus k factorial is m minus k plus 1 factorial. So we have m minus k plus 1 factorial. Okay, and actually, well, this thing that we have here on the numerator, it's equal to m plus 1 factorial. Okay, and I think that this is equal to m plus 1 choose k, right? By definition. Okay, so we are going to rewrite the equation that we have. So that is the m plus 1 derivative of f is equal to u to the m plus 1 times b plus the sum from k equals 1 up to m of u to the m minus k plus 1 b to the k, and then times this, but that is just m plus 1 choose k, and then plus u b to the m plus 1. Perfect. So notice that we can integrate these two elements to this sum just by taking into consideration that this will correspond to the 0th element of a sum, and this will correspond to the m plus 1 element of that sum. So if I write it in this way, the sum from k equals 0 up to m plus 1 of u to the m plus 1 minus k b to the k times m plus 1 choose k, we are already including these two elements that we have here. For the element k equals 0 and k equals n plus 1, right? Perfect. So I think that with this is enough to show the Leibniz theorem, because we have reached the expression that we wanted, that corresponds to the n plus 1 element, right? Actually, that is this expression. So it's exactly the same. So yeah, I think that this proves Leibniz theorem. So what we are going to do now is to use it to calculate the third derivative of a given function, just to show an example of how to use this formula. Okay, so the example that we are going to solve is f of x equals x cubed times sine x. Recall that the Leibniz theorem says that the nth order derivative of f is equal to the sum from k equals 0 up to n, and choose k, and then, well, yeah, u to the n minus k, b to the k, right? In this case, u is, of course, x cubed, and b is equal to the sine of x. So in this case, we want to calculate the third order derivative of f. So n is equal to 3. Perfect. So the third derivative of f is going to be the sum from k equals 0 up to 3 of 3 choose k, u to the 3 minus k, b to the k, which is going to be, so it will be 3 choose 0, u to the 3, b to the 0, plus 3 choose 1, u to the 2, b to the 1, plus 3 choose 2, u to the 1, b to the 2, and then plus 3 choose 3, u to the 0, b to the 3. Okay, so 3 choose 0 is equal to 1. U to the 3 will be the third derivative of x cubed, right? So it will be the third derivative of x cubed. And then b to the 0 is just the function without taking any derivative, right? So it will be sine x. And then plus 3 choose 1, which is 3. Then the second derivative with respect to x of x cubed. And then the first derivative of the sine, which is the cosine of x. Then plus 3 choose 2, which is equal to 3. And then the first derivative of x cubed, which is 3x squared. And then the second derivative of the sine, which is the negative sine. And then plus 3 choose 3, which is equal to 1. The zeroth derivative of x cubed, which is x cubed, and then the third derivative of the sine, which is going to be minus cosine of x. Okay, perfect. So the third derivative of x cubed, it will be 6 sine x, and then plus 3. The second derivative of x cubed, which is going to be 6x times the cosine of x, and then plus, minus, right? 9x squared sine x, and then minus x cubed cosine of x. So we can factor, let's take this 3 sine x out, that multiplies 2 minus 3x squared, and then plus cosine of x, 18x minus x cubed. Okay, perfect. So this was just a quick example of how to use the Leibniz theorem to calculate, well, in this case, the third derivative of a function, which is, again, remember that this is only for the product of two functions, right? So functions that are expressed as the product of two functions. Perfect. So I think that with this, I'm going to finish the lesson right now. Thank you so much for watching.